Lecture we're going to work on material from sections 5, 6, and 7. Previously, we had already had a video lecture on sections 1 and 2, and then the activity 9 was on 3 and 4. We'll review just a little bit of that information in 3 and 4, and then talk about information in 5, 6, and 7. Last time we were really working with the video lecture, during the video lecture of the SN2 mechanism. We started to build up to it, and then we really went into detail in Activity 9. So the Activity 9, really we looked at SN2 mechanism, really understanding it, and one of the things we looked at is the curved arrow mechanism. So you might remember, of course, that the curved arrow really shows electron movement. So I have a little video from your textbook. We'll watch it, and we'll watch as the electrons come in, and then they move from here through the transition state. Notice a double dagger, and then we end up with the products, which is the nucleophile attached to the carbon, and then the leaving group went away. This down here is the same really reaction as here. Just gave you this is a different sense. So let's it's not what I wanted. Let's go back. I'm going to watch this again. So mechanism, again noticing this guy's going to come in, the electron's going to attack here, this is going to go away. Transition state with a double dagger, and it comes through. Alright, so we see here, this thing shows us a couple of things, the curved arrow. We also see that one of the things that we get in an SN2 is that it's substitution, nucleophilic, bimolecular. Alright, so that means that there are two things involved in the rate limiting step. And in this case, the two things are going to be the nucleophile, which comes in, so the OH came in, and then also this substrate, which actually initially had the chlorine attached to it. So it's bimolecular. Why do we say that? Well, if we go back and think about our chapter 14 from Gen Chem, that's where we get the rate is equal to the nucleophile and the substrate, And so both of these are first order, and so it's bimolecular in the sense that both of these affect the rate. That is, increasing the concentration of one increases the rate, or increasing this one increases the rate. Either one of those, increasing them individually would increase the rate. Of course, if we increase them both at the same time, that would definitely increase it. I guess another way of saying it is if we decrease the concentration of this one or that one, that would also decrease the rate. We say that this mechanism is also concerted. All right, so you might talk about in concert. All right, so a concert is sort of a whole bunch of instruments playing together that would be in concert or concerted. We see that, and so that just means that the OH group comes in and attacks the C here together. All right, so it's concerted at the same time that the chlorine's going away. And we also notice that this is what we call backside attack, so the OH group was on the opposite side of the chlorine. So that's referred to as backside attack. All right, so a couple of things. This just reminds us, substitution, nucleophilic, bimolecular. It's two molecules, so hence the biomolecular. There are two arrows, but it is one step. So this all occurs in one step. All right, so we might think of it something like this, that it is two molecules, two arrows, one step. All right, and so this is the SN2 mechanism. And this one occurs, it can occur relatively quickly given the situation, but also it can be slow. All right, so concerted. Now, one of the things to follow up on is this idea of front side or back side attack. All right, so one of the things that we often say is that SN2 reactions are stereospecific. That is, they always happen in the same way. All right, so the idea is this backside that the iodine is on the opposite side of bromine. So that is the backside attack as it's coming in. If the iodine came in this way and the bromine left, that would be a front side attack. But in this case, it is a backside attack or a backside displacement as we move that. Now that helps us to understand a couple of things about this mechanism. All right, so one of the things that helps understood is that whenever we started with like the S enantiomer as the reactant, we would always get the R, the opposite one, as the product. All right, so why would this be? Well, that's because the iodine comes in. It always comes in from the same place, and the Br goes away, and that changes the enantiomer in the stereochemistry from S to R. If the iodine came in from the front and the Br went away, well, then the iodine would just be an S, but in this case, it's opposite. So that helps us with the idea of the front side, back side attack. And so this is backside displacement, and so it always happens in that particular way. You might remember we have this thing called a double dagger, and that indicates that we have this transition state, bonds half forming, half breaking, high energy. So that's one of the things is that we say that's term that it's stereospecific. How do we know it's stereospecific? Again, because we always start with one enantiomer, we always get the opposite, and that means then the mechanism shows that this iodine is a backside displacement. All right, so this sort of formally summarizes what we just said, is that when we have S2-bromobutane, we've used that many times, and it reacts with iodine, we get two theoretical products. With front side, we could get this. With back side, we would get the R. And of course, what we always find is we always get this one, and we never get that guy. All right, so and that's really the key. So again, one of the things to point out is that only is observed, and so all SN2 reactions proceed with inversion of configuration. All right, and so we haven't quite brought that term in yet, but that's inversion of configuration. What that means is that we're taking the S and how the hydrogens and these R groups are, and we're flipping them over. So they come over to this side, and that would be inversion of configuration. So they're sort of angled in this direction, and then they go, because they go through this transition state, they're over there. So we refer to that as inversion of configuration. All right, so front side or back side attack, it's always back side, and that is one of the keys for the SN2 mechanism. And again, to help us understand a little bit more about the stereospecificity that we find for this, this particular figure from page 223, it shows the starting material and how it's transformed into a specific product. All right, and that's stereospecific. And again, by the way, this, I think, this little guy, I'm not sure what that is, but that should be a double dagger. This is showing you the maps of electrostatic potential as compared to the other ones. So again, noticing that the iodine coming in, again, really electronegative. The leaving group here, it's also electronegative. As this comes in and attacks that carbon, notice we have the two electronegative things here, and the iodine goes here and adds on, and then we leave with this particular leaving group, which is another halogen. All right, so that's ultimately important. So this is just, again, results from backside attack, the fact that it's stereospecific, but these maps of electrostatic potential can sometimes help us understand this a little bit better and give us a little bit more detail that we might not see in just a regular configuration. The transition state, so the TS. We can also think about it in an orbital picture, and then also to help us understand a little bit more. So we've talked about this transition state, and again, these figures were corrupted, and so that's a double dagger. Halfway through this SN2 reaction, we have a transition state that has now starting to invert. All right, so what does this mean? Well, it starts off, and this carbon, of course, has 4 single bonds, right, to the R groups, and this one to the halogen. As the nucleophile comes in, these start to move through that inversion of configuration. Halfway through in the transition state, of course, these are all planar. They're moving in this direction, but they're at this point where they're all planar. And in that case, what actually happens is that this carbon has an sp2 hybridized like shape. All right, so we say that it's sp2 hybridized like. Why? Well, this bond is half broken. This bond is half forming. This bond is half broken. And you might say, well, that adds up to one full bond. Well, true, but it's going through a change. And so this is a trigonal planar look to it, so all flat. And so this has an sp2 hybridization, or we might say has sp2 like. All right, because again, it's not fully, all these bonds are broken, but they're broken enough that it's gone through this. right? And so then what we can see then is what this looks like in an orbital diagram. Again, is that this C, it has more of a sp3 hybridized orbital here. But as it gets to this point, notice that the two lobes are the same size. Here, notice they're different, and that's typical. This different look is typical of sp3 hybridized. sp2 with an empty p orbital, or a p orbital that it hasn't hybridized, has more of an equal amount, and that's really what scientists really think, chemists really think that this carbon has, is this p orbital. And so then as the reaction goes away, we end up with this halogen that goes away, and again the carbon rehybridizes. So what we can say is that it really starts off in an sp3 like configuration. As it's going through the transition state, we get this sp2 like hybridization, and then finally when it's done, it has sp3 like. Right, and that's really typical for these sp2 hybridized, these sp2 hybridized carbons that are going through the transition state. Right, so again, starting off with sp3, and then as this is pointing out, we'll return to that sp3 hybridization. So we go through that. All right, so this is helping to explain a lot of the things that we've seen, the experimental evidence, these things that we've seen with with SN2 reactions throughout time. This video is quite nice, where it's actually going to plot. In this case, we have the energy potential here, the reaction coordinate. Remember, this just shows you the potential energy. And so again, higher potential energy means more unstable, lower potential energy means more stable, and that's plotted versus the reaction coordinate, and this is just going from the beginning to the end. It's sort of how our mind works. And again, what we see here is a nucleophile. This is OH minus, and then we see chloromethane, so it's CH3Cl, and we're going to watch it as it comes in and attacks, and we'll watch it on this potential energy curve. All right, so let's take a look at this. All right, so they're both coming together. Notice it's going up the curve to the highest point up here. That would be the transition state that we've been talking about. And then the chlorine goes away, and then the OH is added. So again, anytime we break a bond, we always have to go up in energy. We have to put energy in. We go through that transition state. And then in this case, we go to a lower potential energy, meaning the products are more stable. All right, and so this video helps us see that and helps us track the changes in potential energy. So one of the things is that we can see that what happens, since we're getting this very consistent inversion of configuration in SN2 reactions, that is, they always react in the same way, we can synthesize a specific enantiomer by using SN2 reactions. Because we always start with one configuration and always get another one, this is a really good path to getting a very specific enantiomer. Remember, that might be important because sometimes some drugs, some really industrial reagents, they must be one enantiomer or the other. All right, so some pharmaceuticals, they only work in the body one enantiomer. All right, so sometimes we'll need to do that. How can we make them? Well, SN2 can actually be helpful. So for instance, let's take R2-bromo-octane, all right, so long chain. It's reacted with this HS, this is a thiol group, and then we only get S2-octane thiol produced. And basically the HS is the nucleophile and replaces the bromo group. So let's see how this would work in practice. All right, so we want to maintain the R configuration of the thing that we start with, and we also want to get R here. Well, we know if we just use HS and it comes in and attacks the bromine, we're going to get an S straight away. But that's okay. What we can do is we can actually use two SN2 reactions back to back to get overall the R configuration in, that this is our product. How does that work? Again, double inversion sequence. So first of all, we start off with iodine, and again we have our 2-bromo-octane. The iodine would come in, attack here, the bromo would go away, and we would end up with this nice stable intermediate. All right, so notice it's inversion, R to S, and we would end up with this. And so now if we have this compound, and if we now do a second reaction where we have this as our nucleophile, the HS, it can come in here kick off the iodine, and in the second reaction we would end up with the S really in the same place that we have the Br, and we give these would both have the R configuration. And so this is R2-octane thiol. All right, and so this is the compound that we want, and you don't necessarily have to know this whole naming because you haven't seen thiols before, but you get a sense of looking at this, that this is carbon 1, 2, and then it goes all the way out to 8. On the second carbon there's a thiol. But what you can see is that you can use 2 inversion of configuration reactions to maintain this, because one of the reasons is that the SN2 always happens with backside attack. It is never a front side attack, and so that's helpful. All right, so again, this is how we're going to use double inversion sequence to get net retention of configuration is what we see to get this guy. All right, and so this is the product that we want. And so that's one of the nice things about things being consistent and always happening in the same way, is that we have very predictable patterns that come out of this. One of the things that you might try is just to see, can you draw S2-octane thiol? All right, so if we know what this is, the R, and this is just a connection back to our enantiomer chapter, think about what how you would draw differently this particular S configuration, just as sort of an integration to a former chapter. The last thing that we want to talk about in this last little section is really we want to talk about the leaving group. All right, so the thing that's leaving, because that's going to impact the reaction as well. All right, well, in fact, let's go back. A couple of things that are going to impact the rates. The nature of the leaving group, all right, so how good of a leaving group it is, the nature of the nucleophile, so how strong it is, and the structure of the alkyl portion. All right, so all of those will impact it. Initially here, we're just going to talk about the leaving group and see what the importance of it is and how we can use the leaving group to change or hinder a reaction. So as you see here, really the better the leaving group, and that means it has an easier displacement. All right, so the leaving group ability, as we might often call this, can be correlated to ability to accommodate a negative charge. So that means when the leaving group goes away and is on its own, how easily does it accommodate a negative charge, and how easily can it exist on its own with that negative charge? Some particular species, they don't do very well with a negative charge, and that is they just re-react. And so oftentimes what happens in those cases is that the leaving group starts to leave the substrate and it just re-reacts. It never actually goes away. Iodine is a good one, good leaving group. Fluorine is fluorine as an atom is a poor leaving group, but a fluoride in terms of like methyl fluoride, it's really a poor leaving group. And that's ultimately because fluorines are so electronegative that even though they might want the negative charge, they also want to react. And so when a carbon fluorine starts to break, the fluorine is actually fairly reactive, and so then it just reacts and it never really goes away. Whereas iodine, being large sphere in terms of its electron density, can actually go away. So we can see that in terms of the leaving group ability, so bringing this in, we see that down here, that the leaving group ability that's the best would be iodine, and then bromines next, and then chlorine and fluorine, which ultimately is the worst. All right, so we don't get too many SN2 reactions, if any, that really occur with fluorine because it's such a poor leaving group. So for a reaction to move to progress, we need something that's a fairly good leaving group, and so these typically tend to be some of the better ones. There are other leaving groups. We've mostly focused on halogens, but those aren't the other ones. Halogens happen to be good examples. So if we happen to have one of these guys, this triflate ion or the tosylate ion, these guys are really good leaving groups, ultimately because they can leave the carbon, and they're actually fairly stabilized on their own. That is, the oxygen's fairly electronegative, but not too electronegative. It can hold this negative charge, but then also notice we have these double bonds, so there can be resonance forms through these, which can help to spread out that charge and make this a little more stable. You see that same resonance forms that can appear right here. All right, and so those two kind of help to stabilize it. So both of these are good leaving groups. They also notice that they have multiple atoms. That was one of the points of our Activity 9 handout, can we have leaving groups and nucleophiles more than one atom? And ultimately it's yes. All right, so this is good. And so one of the reasons actually that this one, these are such good leaving groups is that they have multiple atoms and we can spread out that negative charge. We should look at generally what makes a good leaving group, and we find out that weak bases are actually good leaving groups. And what we find out is that the leaving group ability is inversely related to base strength. So a really strong basis, something like an OH minus, would not be a good leaving group because it likes to react fairly well and does not like to break, say, like the carbon-oxygen bond in that particular case. But something else, like an iodine or bromine, which is a weak base, would be a good leaving group. Why are weak bases so good? Because they can accommodate that negative charge, as we're just saying. And so as a result, on their own, they can accommodate those charges, and they're actually fairly stable on their own. So if we look at this table 6.4, we notice that some of the leaving groups, the best ones, are like iodine, bromine, some of the halogens, some of these other groups that we've seen, so better leaving groups. They're also, these acids tend to be stronger acids, and so they tend to have weaker bases. Over here, if we look at the other end of the list, these guys tend to be some of the weakest acids. All right, and then they have correspondingly some of the stronger bases because they're weak acids. They tend to have some of the stronger bases, and these are some of the worst in terms of leaving group. All right, so the leaving groups increases sort of in this direction. This is sort of like a continuous table. All right, so it should come as no surprise that these are all things like water, and all of these are pretty stable on their own, and so that makes them a weak base. One of the ways we can look at that is remembering that our key, pKa, is important here. And remembering, of course, if we go all the way back, that remembering what Ka is. And Ka is really just when we have the products over the reactants. And so if we have something like HA as an acid that gives H plus A minus, A minus, and so then Ka would be the products, the H plus, A minus here, all of this over HA. All right, so the measure of Ka, of course, the stronger the acid, that means there's a larger number here. So if HA is a strong acid, there's going to be lots of this because it delivers those. So if it's a weak acid, then there's going to be a larger number here. Well, we don't often look at just straight Ka numbers. Remember, we'll often look at pKa, which we know pKa is equal to the negative log of Ka. And that's what's plotted in this table is the pKa, or shown in this table really, is the log of pKa. So the things that are the strongest acids are here. So they would have the most negative, and really I guess you can think of the smallest numbers. All right, and so those are the strongest acids, and they tend to have the weakest and they do have the weakest bases, which make good leaving groups. All right, so again, generally speaking, the smaller the pKa, as we go from 38 up to here, and then to more negative, these are going to be for the acids, the stronger acid, and they're going to have the weakest conjugate base, and the weakest conjugate base are good leaving groups. So that would include the halogens that we've seen. So we've basically just used the halogens as good examples. Fluorine, of course, is not, but the rest of these are. All right, so those are some of the things that we can learn here about bases, and we're going to continue this moving forward to understand more about this SN2 reaction.